Welcome back to our micro lessons. Today we're diving into lesson 4, current and resistance. What's actually moving when we flip a switch? At its simplest, electric current is just the flow of electric charge. Think of it like water flowing through a pipe, but with a lot more physics. Here's a fun fact. Due to a historical quirk from Ben Franklin, we say current flows from positive to negative, even though the electrons are moving the other way. You might think electrons race through wires at the speed of light, but their actual speed, the drift velocity, is agonizingly slow, about a millimeter per second. So why does the light turn on instantly? Because the electromagnetic field signal travels near the speed of light, pushing all the electrons at once. But no flow is perfect. Every material has resistance, the opposition to this flow of charge. It's like friction for electricity. Resistance happens because electrons constantly collide with the atoms of the conductor, converting some electrical energy into heat. This brings us to Ohm's law. If you increase the push, the voltage, the current goes up. But if you increase the resistance, the current goes down. Material matters. Metals like copper are great conductors because they have a sea of free electrons ready to move with very little resistance. Insulators, on the other hand, hold their electrons tight. They have such high resistance that almost no current can flow through them. Temperature changes things too. As a metal gets hotter, its atoms vibrate more, making it even harder for electrons to pass through. Resistance increases, but at extreme cold, some materials become superconductors. Their resistance drops to exactly zero. Imagine a current that flows forever without a battery. In a series circuit, resistance is additive. The more bulbs you add in a single line, the more total resistance you create, and the dimmer they get. Parallel circuits are different. By providing more paths for the current, you actually decrease the total resistance. It's like adding more lanes to a highway. This resistance isn't just a hurdle, it's how we use electricity. That heat is exactly what makes your toaster toast and your incandescent bulbs glow. Technically, it's a transfer of kinetic energy. The drifting electrons lose speed to the lattice, and that energy manifests as thermal vibrations, heat. We measure this flow in amperes. 1 ampere is a staggering 6 quintillion electrons passing a point every single second. That's a lot of traffic. Resistance is measured in ohms. It's the constant that defines how much voltage you need to get 1 ampere of current to flow. The hidden truth? Most of the energy isn't actually carried by the electrons inside the wire, but by the fields surrounding it. But that's a story for lesson 9. In daily life, we choose materials for their resistance. High-resistance nichrome wire in your toaster is designed specifically to turn current into heat. In electronics, resistors are used to control the flow, protecting sensitive components like microchips from getting too much current. So, remember the analogy. Voltage is the pressure, current is the flow, and resistance is the pipe's restriction. Simple, yet fundamental. Even though we know electrons are the ones doing the heavy lifting, we'll stick with conventional current for our circuit diagrams. It's the language of engineers. And remember, safety first. High current can be dangerous. It's the flow of charge through your body that causes harm, driven by high voltage. We've been talking about direct current, where charges flow one way, but in your walls, it's alternating current. Charges wiggling back and forth 60 times a second. Even in AC, resistance works the same way. The friction of the wiggling electrons still generates heat and obeys Ohm's law. So there you have it. Current is the flow of charge, resistance is the obstacle, and their relationship defines the electrical world around us. But what happens when those charges start moving? They create something entirely new and powerful: magnetism. Thanks for joining me here at James's Physics 101. Keep questioning, keep learning, and I'll see you in lesson 5 to talk about the power of magnets. Stay tuned, and don't forget to check out the rest of the Electromagnetism series. See you next time.